GCE Advanced Level Chemistry Practical Series Experiment number 32. Experimental determination of the order of the reaction with respect to ferric ions for the reaction between Fe3+ and iodide ions. The aim of this experiment is to determine the order and the rate expression of a reaction experimentally. Now, let's move on to identifying the chemicals and the equipment we will be using for this practical. Let's identify the chemicals and the equipment we will be using for this experiment. We will be using potassium iodide solid, and we'll be preparing a potassium iodide solution with the use of potassium iodide solid. We'll be using ammonium ferric sulfate, or you may also see it written as ammonium iron sulfate, sodium thiosulfate, and starch. Using the starch that we have over here, we'll be preparing a starch solution. We have a starch solution prepared here. Apart from that, we'll be using 1 moles per decimeters cube sulfuric acid, distilled water, and as equipment, we'll be using volumetric flasks to prepare the solutions we need for this experiment. Apart from that, we'll be using a digital balance to weigh the correct masses of these solids that we need to prepare the solutions that we need for this experiment. And we'll be using beakers. As you can see, the beakers are labeled. We'll be using a stopwatch, and we'll be using a funnel. And apart from that, to measure the correct volumes of each of the solutions we need for this experiment, we will be using burettes as well. So students, we have now identified the equipment and the chemicals we'll be needing for this experiment. Now it is time for us to move on to the next step of our experiment. Now students, when we are carrying out this experiment, we need 3 different solutions: potassium iodide solution, ammonium ferric sulfate solution, and sodium thiosulfate solution. In this first part of our experiment, we are going to be preparing potassium iodide solution. The concentration of the potassium iodide solution we need is 3 moles per decimeters cube, or we can say 3.0 moles per decimeters cube. And we are going to prepare 100 milliliters of this solution. So we have our potassium iodide solid here. So we need to measure the correct mass of potassium iodide solid. We need to prepare this 3.0 moles per decimeters cube concentrated potassium iodide solution. So since we are going to be preparing only 100 milliliters of this solution, we can carry out a calculation and we can find the number of moles of potassium iodide that should be present in the medium. Since we have a concentration 3.0 and the volume is 100 milliliters, you would find the number of moles we need is 0.3 moles. And since we know the molar mass of potassium iodide, which happens to be 166 grams per mole, we can calculate the overall mass that we need to prepare this solution. So when you use the molar mass and the number of moles we need, the mass that we should measure is going to be 49.8 grams. We obtain that value by multiplying the number of moles, which is 0.3 moles, by the molar mass, which is 166, and you got to 49.8 grams. So we are going to measure 49.8 grams of potassium iodide with the use of our digital balance here. So let's turn on the digital balance. We have the digital balance turned on, and we can see it reads 0, and the unit that we are using is grams. Since 49.8 grams is a substantial mass, we are not going to measure it into watch glass. We can straight away measure it into a small beaker, dissolve it sufficiently, and then we can transfer it to a volumetric flask. So let's directly measure this 49.8 grams of potassium iodide into a beaker. So beaker has its own mass. We are going to use the tare function to cancel that mass out. Now you can see the digital balance reads 0. Then we can take our potassium iodide solid and measure exactly 49.8 grams of potassium iodide. Now students, as you can see, we have measured 49.81 grams. So after measuring 49.8, or in this case 81 grams, we can move on to dissolving this amount of potassium iodide with water. So since transferring this whole amount of potassium iodide into a volumetric flask could be difficult, we are going to dissolve it with the use of a little bit of distilled water first, and then we'll be moving on to transferring this into a volumetric flask. So we have our funnel and the wash bottle here. We will add a small amount of water and we'll try to dissolve as much of this potassium iodide as possible. And then we will transfer that into our volumetric flask. We'll have to add a little bit more water. Be mindful when you're adding water, because we are trying to prepare a 100 milliliter solution. If you add more than 100 milliliters of water here, then you will not be able to prepare 3 moles per decimeter cube concentrated potassium iodide. Your concentration will be slightly more different to what you want. Now students, if you observe here, we have dissolved all of the potassium iodide we added, and we have not added over 100 milliliters of water. Actually, it is under 100 milliliters of water in this beaker. But you can make a good observation here. You can see that the beaker is now very cold, and you can visually observe that as well, because you can see the water vapor is starting to condense around the outer walls of the beaker. So this indicates that the solution in the beaker is quite cold, and this happens because dissolving potassium iodide in water to form potassium iodide aqueous solution is an endothermic process which results in a temperature decrease when we are dissolving potassium iodide in water. So we have dissolved all of the solid. Now we can see, students, all of the solid that we took into this beaker has completely dissolved in water. So it is time for us to transfer that into our volumetric flask. We have a volumetric flask labeled 3.0 moles per decimeters cube, a concentrated potassium iodide solution here, and we are going to use that volumetric flask. So this volumetric flask has a volume of 100 milliliters. So we will be transferring this solution into this volumetric flask. After transferring the liquid into the volumetric flask, we can rinse this beaker one more time with a little bit of distilled water to make sure all of our potassium iodide is transferred into the volumetric flask. We can repeat it once. Afterwards, students, we can very carefully wash the internal walls of the funnel as well. Now by this point we can see we are very close to the calibration mark. Our water level is over here, calibration mark is all the way over here. So we will slowly start adding distilled water until the meniscus aligns with the calibration mark. So to observe the calibration mark and the meniscus, you can bring this to our eye level. And by now we have added the right amount of water, and the bottom of the meniscus aligns perfectly with the calibration mark. Now students, we will place the stopper and close it tightly. After placing the stopper, you can turn it upside down a few times like so to make sure the solution is completely mixed. Now students, we have prepared a potassium iodide solution with 3.0 moles per decimeters cube concentration. So we can set it aside, and now we can move on to the next solution. Now students, we are going to observe how ammonium ferric sulfate solution is going to be made. This experiment observes the order of the reaction when we are reacting Fe3 plus ions with iodide ions. So we saw earlier, in the early part of this experiment, we prepared a potassium iodide solution to introduce iodide ions into the medium. And in this part of our experiment, we are going to prepare an ammonium ferric sulfate solution to introduce Fe3 plus ions into the medium. So we have our ammonium ferric sulfate, or ammonium iron 3 sulfate solid sample here, and this particular solid sample is a hydrated sample, so the formula would be ammonium ferric sulfate 12H2O, and the molar mass is 482.19 grams per mole. We aim to prepare a solution of 0.1 moles per decimeters cube concentration, and the volume would be 250 milliliters. When you do the calculation, you would observe the number of moles we need is 0.025 moles, and the mass we should measure, given that the molar mass is 482.19 grams per mole, the mass we should measure is 12.05 grams. The mass we should measure is 12.05 grams to prepare 0.1 moles per decimeters cube concentrated ammonium ferric sulfate solution. So let's move on to measuring that mass. We have our digital balance here. We'll turn it on again. We can see the unit is in grams, and we are going to place our watch glass on top of the balance, and then we can use the tare function to get to a zero reading on the digital balance. Afterwards, we will be measuring 12.05 grams of ammonium ferric sulfate or ammonium iron 3 sulfate. We are going to measure 12.025 grams. We are going to measure 12.05 grams. Now students, we have measured 12.05 grams. Now students, after measuring this 12.05 grams of ammonium ferric sulfate, we have to dissolve this in 1 moles per decimeters cube concentrated sulfuric acid to prepare the solution we want. What we need is 0.1 moles per decimeters cube concentrated Fe3 plus iron solution, but not just any Fe3 plus iron solution. We need acidified Fe3 plus iron solution. So we are going to dissolve this ammonium ferric sulfate that we measured over here in 1 moles per decimeters cube concentrated sulfuric acid. Since it can be a little bit difficult to dissolve this ammonium ferric sulfate in sulfuric acid or in aqueous mediums in general, we can use a small beaker, and we are going to transfer this ammonium ferric sulfate into the beaker and then dissolve the ammonium ferric sulfate up to a certain extent in the beaker, and then we'll be transferring into the volumetric flask, and we'll be preparing our ammonium ferric sulfate, not just any ammonium ferric sulfate, acidified ammonium ferric sulfate solution in a 250 milliliter volumetric flask. So like I mentioned earlier, we cannot use water, so we'll be using 1.0 moles per decimeter cube concentrated sulfuric acid solution. So this is 1.0 moles per decimeter cube concentrated sulfuric acid that we have over here, and we'll be transferring first this solid into a beaker like so. And then we can proceed to wash the watch glass with some sulfuric acid. After transferring it into a beaker, we can start to dissolve the ammonium ferric sulfate solid by stirring it. So we are dissolving the ammonium ferric sulfate in sulfuric acid. We can add a little bit more sulfuric acid. Now, as you can see, students, the color of the solution is starting to change. That is because Fe3 plus ions are coming into the medium. And you can see majority of the ammonium ferric sulfate solid is dissolved in the medium. We will add a little bit more sulfuric acid since we are preparing a 250 milliliter solution. When you're adding sulfuric acid, you can add sulfuric acid all the way up to about 150 milliliters. You don't have to worry. Then afterwards, we can add ammonium ferric sulfate little by little into the volumetric flask after transferring this portion of the solution into the volumetric flask. Now, students, after dissolving all of the ammonium ferric sulfate solid in a small amount of water, we can now transfer this ammonium ferric sulfate solution into our volumetric flask. So this volumetric flask is labeled acidified 0.1 moles per decimeter cube concentrated ammonium ferric sulfate. So you shouldn't forget the fact that we prepared this ammonium ferric sulfate by dissolving the ammonium ferric sulfate solid in 1 moles per decimeter cube concentrated sulfuric acid. So now we are going to transfer this into our 250 milliliter volumetric flask. Then we can wash our beaker with a little bit of sulfuric acid to make sure all of the ferric sulfate is taken from the beaker into the volumetric flask, and we can wash the funnel as well. We can carry out another washing. And finally, we can start to add sulfuric acid all the way up to our calibration mark. So when you're adding the last bit of sulfuric acid to this volumetric flask, we can use a dropper and we can transfer the last few drops of sulfuric acid with the use of a dropper. We have our calibration mark up here, and we have quite a bit of sulfuric acid to add. So we can use the beaker, and then towards the final parts we can add sulfuric acid using a dropper. When we're adding the final few drops, we can add the final few drops of sulfuric acid with the use of a dropper like this. And as soon as the bottom of the meniscus aligns perfectly with the calibration mark, you can stop adding sulfuric acid, and we have now prepared our 0.1 moles per decimeter cube concentrated acidified ammonium ferric sulfate. But we have one more step to go. We have to close the stopper here, and then we have to mix the solution really well. You can turn it upside down a few times to make sure the solution is mixed really well. So by now we have prepared our acidified 0.1 moles per decimeter cube concentrated ammonium ferric sulfate solution. Let's move on to the next step. Now we move on to preparing another solution, which is sodium thiosulfate solution. The concentration of the solution we are going to prepare is 0.06 moles per decimeter cube. So for this experiment, we need a sodium thiosulfate solution of 0.06 moles per decimeter cube, and the molar mass of sodium thiosulfate 5H2O, which we have over here. The solid that we have over here is sodium thiosulfate, or Na2S2O3 5H2O. So the molar mass of this is going to be 248.17 grams per mole, and we need to prepare a solution that has concentration of 0.06 moles per decimeter cube, and we are going to prepare it to this volumetric flask. So this is 250 milliliter volumetric flask. So if you calculate the mass that you need to measure to prepare the solution we need for this experiment, the mass would come up to 3.72 grams. So we need to measure 3.72 grams and then proceed to preparing the solution with the use of a volumetric flask. So like we did in the previous instances, we will use our digital balance here, and we will be using a watch glass as well. So let's use the tab function to get the digital balance reading to 0 after placing the watch glass on the digital balance. And then we have our sodium thiosulfate 5H2O over here, and we need to measure exactly 3.72 grams. So let's proceed to measure exactly 3.72 grams. Now we have measured 3.72 grams, as you can see here. And now we can leave the sodium thiosulfate solid bottle aside. And then we can transfer this sodium sulfate solid into our volumetric flask that we have over here. In order to do that, we'll be using a funnel and a wash bottle filled with distilled water. Now we are going to transfer this solid with the use of a wash bottle this way. We have learnt about transferring solids in the following manner in previous experiments. we need to wash the watch glass after transferring the liquid like so. We can turn the watch glass upside down as well and wash the bottom bits of the watch glass as well. And then we can wash the inner walls of the funnel as well as the tip of the funnel. Then we can keep the funnel aside. Then we can mix the contents in the volumetric flask before we proceed to add more water to the volumetric flask. You can see all of the sodium thiosulfate has now completely dissolved. You can see in here sodium thiosulfate has completely dissolved. So now we can proceed to add more and more water. You can use a beaker as well. Now students, we have added water up to this level in the volumetric flask. We have to add water all the way to this calibration mark. And in order to do that, we can use the wash bottle. But after getting quite close to the calibration mark, we can use a dropper. At this point, students, the meniscus aligns perfectly with the calibration mark. Now, afterwards, you can place the stopper and closely tighten the stopper and place one finger on the topper, and then we can start mixing the contents in this volumetric flask by turning it upside down a few times like this. This is to ensure that we produce a homogeneous solution where the concentration throughout the solution is going to be the same. So now students, we have prepared 3 different solutions we'll be needing for this experiment. Now students, it is time for us to move on to the next part of the experiment where we will be actually conducting this experiment and observing the time taken for each reaction to take place. So let's move on to the next part of this experiment. Now students, we are going to be measuring different solutions into these 2 beakers. And before we proceed to that, let's understand what is taking place in this experiment. In this experiment, we are trying to observe the order of the reaction in a reaction between I- ions and Fe3+ ions, or in other words, iodide ions and ferric ions. The reaction between iodide and ferric ions results in forming I2 and Fe2+ ion solutions. So students, when this reaction is taking place, we need to measure the rate of the reaction when we change the concentration of Fe3 plus ions. So in the first part of our experiment, we are going to be changing the concentration of Fe3 plus ions. We are going to start with a higher Fe3 plus concentration, and we are going to carry out 5 different experiments where the Fe3 plus ion concentration is gradually decreased. So when we are carrying out these 5 experiments, we need a way to measure the rate of the reaction for each of these experiments. In this particular reaction, iodine is produced. So we can use the time taken to produce a certain specific amount of iodine to be produced. So that is going to be the measure that we are going to use to measure the rate of the reaction. So we are going to observe how long it takes for the reaction to produce a certain amount of iodine to be produced. So how can you know when a certain amount of iodine is produced? Now this can be achieved by a second reaction. If you have a reaction between I2 and sodium thiosulfate, you know I2 is going to be turned into I- ions and tetrathianate ions. So I2 turns into I- and thiosulfate turns into tetrathianate. So what we are going to do in this experiment, we are going to take to beaker 1 Fe3 plus ions, and to beaker 2 we will be taking potassium iodide solution along with thiosulfate ion solution. So we are going to measure a very specific amount of sodium thiosulfate into this. So in each of the experiments we are going to be doing from now onwards, the amount of sodium thiosulfate we take into this beaker 2 will be the same. Then after we add potassium iodide and a very specific amount of sodium thiosulfate, we are going to add starch indicator here as well. And then we will use a stopwatch as well, and then we will mix contents in beaker 1 with beaker 2. When you do that, students, potassium iodide comes into contact with Fe3 plus, or iodide ions come into contact with Fe3 plus ions in the medium, and the main reaction we are interested in will happen, and it will produce iodine. And this medium has starch. So iodine will react with starch, right? And will produce a blue-black color. However, students, iodine won't get a chance to produce a blue-black color with starch, because in this medium, sodium thiosulfate, a specific amount of sodium thiosulfate is also there. So iodine that is produced will first react with the sodium thiosulfate that is in the medium. So as the main reaction happens, the produced iodine will first have to react with the sodium thiosulfate, and after all of the sodium thiosulfate is reacted in the medium, then the next produced iodine will show a color change. When it reacts with starch, a blue-black color change will be observed. So sodium thiosulfate in the medium will delay this color change, and it will also make sure that a certain amount of iodine is produced before we observe the color change. So this helps us to measure the time taken for measuring a very specific amount of iodine to be produced. So since the amount of sodium thiosulfate in the medium does not change from reaction to reaction, we are always going to end up producing the same amount of iodine before a color change is observed. So in this case, in simpler words, we are going to observe the time taken for a certain amount of iodine to be produced when we keep on changing the concentration of Fe3 plus ions. So students, with that in mind, we are going to be moving on to measuring the different solutions we need to be taking into each of these beakers. As I mentioned earlier, to beaker 1, we need to measure our Fe3 plus acidified Fe3 plus ion solution. So if you take a look at your lab manual that you have with you, for the first reaction, you need to take 25 cubic centimeters of acidified 0.1 moles per decimeters cube concentrated Fe3 plus ion solution. So we have filled Fe3 plus ion solution into this burette all the way to the 0 point. So we prepared our Fe3 plus ion solution earlier on, and now we have filled it into this burette. So we will now use the burette to obtain exactly 25 cubic centimeters of this solution. Now keep in mind, students, we will not be using this burette throughout this practical, in the sense we will not show you the measuring of each of these solutions throughout this practical. We will be doing that off camera in the next repeats of this experiment, but this first reaction we will show how the measuring of different solutions are going to be done with the use of a burette. So we are using a burette so that we can obtain a more accurate volume into these beakers. We need to measure exactly 25 cubic centimeters. Right, so exactly 25 cubic centimeters of Fe3 plus, acidified Fe3 plus, is measured into beaker 1. We'll keep it aside. And then, students, we can actually move on to the next burette. So the next burette that we have over here contains our potassium iodide solution. It's filled all the way to the top. So if you take a look at our potassium iodide solution here, and if you take a look at your practical or lab manual, you would observe you need to take 10 cubic centimeters of potassium iodide solution into beaker 2. So let's proceed to take 10 cubic centimeters of potassium iodide, 10 cubic centimeters of potassium iodide into beaker 2. We have measured exactly 10 cubic centimeters of potassium iodide into beaker 2 now. So after measuring 10 cubic centimeters of potassium iodide into beaker 2, we need to also measure exactly 15 cubic centimeters of our sodium thiosulfate solution. Now, students, one thing to note before we actually measure the sodium thiosulfate solution is, in the lab manual of your practical handbook, the concentration of sodium thiosulfate that is recommended is 0.006, and we have taken a slightly higher concentration because this will allow us to observe the reaction in a more clear manner, because if the concentration of sodium thiosulfate is very small, then the delaying of the color change is going to be very small. Higher the concentration, higher the amount of sodium thiosulfate moles in the solution, which will lead to a greater delay after we add the solutions together. There will be a greater delay in displaying the color change. So this will allow us to measure a more clear time change. So we have increased the concentration to 0.06. After making notice of that, we have our sodium thiosulfate solution taken into this small beaker, and we are going to measure 15 milliliters of this solution. Now, students, we have measured exactly 15 cubic centimeters of sodium thiosulfate. And keep in mind, thiosulfate ions do not interfere with the reaction between I- and Fe3+. between I minus and Fe3 plus does not show reaction with thiosulfate ions. So thiosulfate ion being present in the medium will not change the main reaction that is happening in this experiment. Now let's transfer these 25 cubic centimeters of sodium thiosulfate into our beaker 2. Now the beaker 2 contains 15 cubic centimeters of our sodium thiosulfate solution and 10 cubic centimeters of potassium iodide solution. The concentration of potassium iodide solution we prepared was 3.0 moles per decimeters cube. Now we can move on to add starch solution as well. We have our starch solution here, and we can add roughly about 5 drops of starch solution into this beaker 2. So students, we have now taken the correct solutions into these 2 beakers. It is time for us to mix it, and then as soon as we mix it, we are going to use a stopwatch and we are going to measure the time taken for the color change to happen. Now students, when you are doing this, it is better if you can stir the solution. So to stir the solution, you can use a glass rod or you can use a magnetic stirrer. So it is optional. If you have a magnetic stirrer with you, you will be able to use it. However, if you don't have one, stirring the solution will aid proper mixing of the reagents. It will result in obtaining a more accurate time for the color change to take place. So now students, let's move on to the part where we will be mixing these 2 on a magnetic stirrer. Now students, we have our magnetic stirrer in front of us here. So magnetic stirrers comes with a small magnet like this, a small magnetic rod, and beneath this pan there's another magnet which will help in spinning this magnet that we have on top of this surface. For example, if you turn this magnetic stirrer on and if you give it a little bit of power, you can see the magnet on top of this pan is starting to rotate. So this will allow the correct mixing of the solution. So we can now take these magnets and we can place it in our beaker 2, and then we can turn on the magnetic stirrer. You can see the contents in beaker 2 are now being mixed really well. At this point, we can proceed to add the contents in beaker 1. As soon as you add the contents in beaker 1, keep in mind you need to start the stopwatch. The stopwatch is now reading 0, and as soon as you add the contents in beaker 1 to beaker 2, you need to start the stopwatch. And then as soon as you see the color change, you need to stop the stopwatch. Now we are going to add contents in beaker 1 to beaker 2 and we are going to start the stopwatch. It took exactly 2 seconds. It took exactly 2 seconds for the color change to appear. I hope you observed that sudden color change that comes about as soon as all of the sodium thiosulfate in the medium is reacted with I- ions in the medium. So students, the time measured is 2.00 seconds. 2.00 seconds. Now let's move on to the second step of this experiment. And now students, we are going to change the concentration of Fe3 plus ions in the medium. So how are we going to do this? So the reaction mixture was prepared in the previous reaction by mixing 25 cubic centimeters of Fe3 plus ion solution with 15 cubic centimeters of sodium thiosulfate and 10 cubic centimeters of potassium iodide. So when all of these reactants were added together, the overall volume of the medium was 50 cubic centimeters. So we are going to start changing the concentration of Fe3 plus ions in the medium by decreasing the volume of Fe3+ that we take into the final reaction mixture. So initially we measured 25 cubic centimeters of Fe3+. Now in the second reaction we are going to only take 20 cubic centimeters of Fe3+. So students, there's a 5 milliliter reduction of the Fe3+ solution we take into the reaction mixture. This means the reaction mixture also goes down by a volume of 5 milliliters. So this brings in a variation to the volume of reaction mixture, which is not something we want. So to keep the reaction mixture volume a constant, we are going to add distilled water, so that every time we decrease the concentration of Fe3+, to make sure the reaction mixture has the same volume, we will be adding different volumes of water. In this case, since we are going to be decreasing the concentration of Fe3+ by adding 5 milliliters less of the Fe3+ solution into the reaction mixture, we need to add 5 milliliters of water to make sure the final reaction mixture has 50 milliliters. So the second reaction mixture is going to be consisting of 10 milliliters of potassium iodide, 15 milliliters of sodium thiosulfate, and 20 milliliters of Fe3+ ion solution. So this will bring the total volume to 45 milliliters. But if you add 5 milliliters of distilled water, the overall reaction mixture will have a volume of 50 milliliters. And this also brings about the decreasing of our Fe3+ ion concentration. So students, after going through that part, now we are going to observe what we will be doing here. So we have already measured 20 milliliters of acidified Fe3+ ion solution over to beaker 1. So the initial concentration of the solution that we prepared in the previous parts of this experiment was 0.1 moles per decimeters cube concentration. So we are going to add this Fe3+ ion solution, or actually 20 milliliters of this Fe3+ ion solution, into beaker 2. So beaker 2 contains, in this situation we only have in the beaker 2 our potassium iodide solution, 10 cubic centimeters of potassium iodide solution. And to this we need to add 15 cubic centimeters of our sodium thiosulfate solution. We have already measured it. We have measured 15 cubic centimeters of sodium thiosulfate solution, and we will be adding this to our beaker 2. And then, like I mentioned earlier, we need to add distilled water as well. So we have measured 5 milliliters of distilled water into this measuring cylinder, as you can see, and we are going to add that also into our beaker 2. So like we did in the previous experiment, we are going to place this beaker 2 on our magnetic stirrer, and then we can turn this on, and we will be adding contents of beaker 1 into the contents of beaker 2 here. Before we do that, don't forget to add the starch solution as well. We need to add 5 drops of the starch solution. And then we'll be moving on to adding our contents on beaker 1. So students, when you are adding contents in beaker 1, which is Fe3+ ion, as soon as you add it, turn on your stopwatch. So we started the stopwatch, and as soon as you see a color change, we need to stop the stopwatch. I hope you were able to observe the color change as well as the time taken for the color change. So it took 8.10 seconds. It took 8.10 seconds for this color to be observed. You can see the color change as well as the time here. So for the first Fe3 plus ion concentration, the time taken was 2 seconds. For the second one, it was 8.10 seconds. Now let's move on to the third step. Now students, we are in the third reaction. So in the third reaction, we have taken a volume of 15 cubic centimeters of acidified Fe3 plus ion solution, and into this beaker 2 we have measured potassium iodide. We have measured exactly 10 cubic centimeters of potassium iodide. So throughout these 5 reactions, we will not change the volume of potassium iodide that we take into the reaction mixture, and we will only be changing the volume of Fe3 plus ion solution we will be taking to the reaction mixture. To keep the reaction mixture at a constant volume, we will be adding varying volumes of water. So keep in mind, potassium iodide, sodium thiosulfate volumes do not change in the first 5 reactions we will be carrying out here. However, we will be changing the Fe3 plus ion solution's volume that we take into this reaction mixtures. So in this case, we have 15 cubic centimeters of Fe3 plus and 10 cubic centimeters of potassium iodide measured into beaker 2, and 15 cubic centimeters of Fe3 plus aqueous ion solutions measured into beaker 1. And we are going to proceed to add our sodium thiosulfate solution. We have already measured it. That's 15 cubic centimeters of sodium thiosulfate. We are going to add it to our beaker 2. And we have measured 10 cubic centimeters of distilled water. So we have a measuring cylinder here. Let's measure 10 cubic centimeters of distilled water. And I want you to know why we measure 10 cubic centimeters of distilled water. When we were measuring Fe3 plus aqueous ion solution, we have only measured 15 cubic centimeters of Fe3 plus aqueous ion solution. So we have 15 cubic centimeters worth of volume here, and then in the beaker 2 we have 10 cubic centimeters of potassium iodide and 15 cubic centimeters of sodium thiosulfate. So the overall volume in beaker 2 right now is 25 cubic centimeters. And if you add this 10 cubic centimeters of water into beaker 2, now the volume is 35 cubic centimeters. So 35 plus 15 is 50 cubic centimeters. So keep in mind students, throughout these 5 reactions, you will observe that the overall volume of the reaction mixture is going to be kept at 50 cubic centimeters. And that is why we are going to be adding varying volumes of water. As we decrease the volume of Fe3 plus we take into the medium, the volume of water that we take into the medium will be increased. So as we did before, we will be placing this stirring rod over here, and we can start mixing the reactants together, and we'll be adding 5 drops of starch solution as well. So after that, we are going to be adding our beaker 1 content into this beaker 2. Now students, as we add the Fe3 plus aqueous ions or acidified Fe3 plus aqueous ions into the medium, we will start our stopwatch. So the color change was obtained at 18.41 seconds. So the color change was obtained at 18.41 seconds. Now students, we are going to be moving on to the fourth reaction. Now we move on to the fourth reaction. In the fourth reaction, we have decreased the volume of Fe3 plus ion solution. We have taken once more. So the first reaction we took 25 cubic centimeters of the Fe3 plus ion solution, and then in the second one we took only 20 milliliters, third we took 15, and now when it comes to the fourth reaction, we have taken 10 cubic centimeters of acidified Fe3 plus ion solution with the initial concentration of 0.1 moles per decimeter cube. So to this beaker 1, we have taken a 10 cubic centimeters of Fe3 plus ion solution. And to beaker 2, like I mentioned in the third part of this experiment, we have taken only 10 cubic centimeters of potassium iodide solution. And the solution's concentration was 3.0 moles per decimeter cube. And we have measured 15 cubic centimeters of sodium thiosulfate, and we are going to add it to our beaker 2. And then to keep the volume a constant, we have to add 15 milliliters of distilled water. So we have measured 15 milliliters of distilled water into this measuring cylinder, and we are going to be adding this 15 milliliters of distilled water again into beaker 2. Now students, we can add the starch solution here to beaker 2 as well. So we are going to add 5 drops of starch solution into our beaker 2, and like we did in the previous parts, we are going to add our magnetic stirrer bar into the beaker, and then we are going to turn on the magnetic stirrer, and all that is remaining for us to do now is to add Fe3 plus ion solution. So we have our beaker 2 containing our Fe3 plus ions, and we are going to start the stopwatch as we add this into the beaker 1. We will have to wait till the color change is given. It's at 30 seconds now. One minute. Color change was given at 1 minute 26 seconds. 1 minute and 26 seconds. So the overall time taken for this color change to appear is 86.13 seconds. 86.13 seconds. So the overall time that it took for this reaction to show a color change was 86.13 seconds. It took 86.13 seconds, or in other words, 1 minute and 26.13 seconds. Let's move on to the fourth reaction. Now students, we will be repeating the same steps for the fifth experiment as well, but in this experiment we will be taking only 5 cubic centimeters of Fe3 plus acidified Fe3 plus ion solution. So we will be measuring 10 cubic centimeters of potassium iodide into beaker 2, and then we have 15 cubic centimeters of sodium thiosulfate measured into this measuring cylinder. As you can see, we'll be transferring it into beaker 2. And since we are taking only 5 cubic centimeters of Fe3 plus, we need to take 20 cubic centimeters of distilled water. So we have 20 cubic centimeters of distilled water measured here. We'll be adding that as well. And then all that is left for us to do is to mix these two together. And so let's keep in mind, when it comes to these two reagents, their main reaction is between I minus and Fe3 plus ions, and the produced I2 will react with a specific amount of thiosulfate ions that are in the medium. However, in this particular scenario, since we have increased the concentration of sodium thiosulfate into 0.06, the amount of sodium thiosulfate that is in the medium will be greater than the amount of I2 that is going to be produced when only 5 milliliters of our Fe3 plus ion solution is added to this. So the total amount of I2 that is produced is not going to be sufficient to produce a color change in this reaction mixture, because all of the I2 that is produced gets reacted with the thiosulfate ions in the medium, because the amount of I2 produced will be lower than the amount of thiosulfate ions that are present in the medium. This was not the case when it comes to the previous 4 instances, but in this 5th reaction, you will observe, even if we keep the reaction going on for about 5 minutes, you will not observe a color change. This is because the amount of I2 produced is lower than the amount of thiosulfate ions that are present in the medium. However, we will observe this so that we can be very sure. So we will mix these reactants together, and then we will turn on the stopwatch, and we will see if we are going to get to a color change at least within 5 minutes. This, if we don't observe a color change at least within 5 minutes, we can be sure that there's no color change going to be present, because like I mentioned earlier, if you do the calculations, you will see for yourself that the amount of iodine produced is going to be lower in number of moles than the number of thiosulfate that are going to be present in the medium. So in this case, actually the number of sodium thiosulfate that are present in the medium is more than sufficient to react with all of the I2 that is produced when we mix only 5 milliliters of the Fe3 plus aqueous ion solution into this medium. So students, in summary, since the amount of thiosulfate ions present in the medium is more than sufficient to react entirely with the I2 that is going to be produced when these two reagents are mixed, we will not see a color change. So in this case, the produced I2 runs out before we run out of thiosulfate ions. So while keeping that in mind, we will move on to this reaction. So we need to add starch solution as well. So let's add starch solution. And now it is time for us to add contents in beaker 1 to beaker 2. So let's turn on the magnetic stirrer, and then we are going to add this Fe3 plus ion solution and start the stopwatch. And we will let this go on for about 5 minutes, and I will come back to talk about why we didn't see an observation once more. Now students, it has been 5 minutes and as you can see, no color change. So as you can see over here, there is no color change. This indicates that the potassium iodide, when reacted with Fe3 plus, it produced iodine. However, the produced iodine was not sufficient enough to react and completely finish the amount of sodium thiosulfate that is present in the medium. Therefore, we do not see a color change here because the amount of thiosulfate ions present in the medium was more than sufficient to react with all of the I2 that is produced through this reaction. So there was no remaining I2 to react with the starch that we added to this aqueous medium. So that is the end of part A of this experiment. So let's move on to the part B of this experiment. In the first part of our experiment, we saw how the change in the concentration of Fe3 plus ions in the medium affected the rate of the reaction. So the rate of the reaction was measured by measuring how long it took for an equal amount of iodine to be produced when we change the concentration of Fe3 plus ions. So we kept on changing the concentration of Fe2 plus ions in 5 different solutions, and we saw how the time taken for the same amount of iodine to be produced increased as we decreased the Fe3 plus ion solution concentration. So now in this second part of our experiment, we are going to be observing how changing the I minus or iodide ion concentration affect the rate of the reaction. So in this case, we are going to be changing the concentration of I minus by taking smaller and smaller volumes of I minus into the reaction mixture. We saw in the very first reaction of the first part of our experiment, we took 10 cubic centimeters of iodide ion solution, 25 cubic centimeters of Fe3 plus ion solution, and 15 cubic centimeters of our sodium thiosulfate solution. So there's no need to repeat that particular reaction. However, from there onwards, we are going to be seeing if you bring down the volume of iodide ion solution up to 8 cubic centimeters and then carry out this reaction. And the third one would be to bring down the iodide ion concentration to 6 cubic centimeters in the reaction mixture. And you're going to continually decrease the iodide ion concentration and observe whether the rate of reaction change when we change the concentration of iodide ions in the medium. So the very first reaction we'll be carrying out is by mixing 25 cubic centimeters of Fe3 plus aqueous ion solution in this beaker 1 with 8 cubic centimeters of iodide ion solution in this beaker 2. So in these 4 reactions we will be doing today under the part 2 of this experiment, we will not be changing the volume of Fe3 plus ions we are going to be using in this part 2. However, we will be changing the volume of I minus ions solution we will be using for this part. So potassium iodide, we have only taken 8 cubic centimeters here, and as you know, like we did in the previous parts, we have to add 15 cubic centimeters of sodium thiosulfate. So we have already measured 15 cubic centimeters of sodium thiosulfate here, and we will be adding that to our potassium iodide solution. And since we have decreased the volume of potassium iodide solution we take by 2 cubic centimeters, we have to replace that 2 cubic centimeters by adding distilled water. So here we have 2 cubic centimeters measured. This is distilled water, and we will be adding these 2 cubic centimeters of distilled water into beaker 2 as well. Now students, all that we have left is to add these two together and start our reaction. So we will place our beaker 2 on the magnetic stirrer, and we include the stirrer bar there, and then we can add our starch solution as well. We can add 5 drops of the starch solution, and then we can turn on our magnetic stirrer. Now, after turning on our magnetic stirrer, we can proceed to add contents in beaker 1 to beaker 2, and as we did in the previous instances, we will be starting the stopwatch. The reading comes to 3.22. Reading comes to 3.22. So the color change was obtained at 3.22 seconds. 3.22 seconds. Now, let's move on to the next part. Now students, we move on to the second reaction in part B, In this reaction, we have decreased the iodide ion concentration yet again by taking only 6 decimeters cube of iodide ion solution we prepared earlier. So we have only 6 decimeters cube of iodide ions taken into this beaker 2, as you can see. And then in beaker 1, we have 25 cubic centimeters of acidified Fe3 plus ion solution with a concentration of 0.1 moles per decimeters cube. So since we have decreased the volume of potassium iodide we take for this reaction, we have to add a little bit of more water to bring the total volume up to 50 milliliters. So we have added 4 milliliters of water into this measuring cylinder. As you can see here, this is distilled water. So we can transfer that into our beaker 2. And like we did in the previous experiments, we are going to add 15 cubic centimeters of sodium thiosulfate solution also into this beaker. Apart from that, students, we are going to add our starch solution into the beaker 2 as well. We'll add 5 drops of starch solution into the beaker, and then we can place it on our magnetic stirrer, and we can start the magnetic stirrer like so. Now it is time for us to add our Fe3 plus aqueous ion solution. So as we add Fe3 plus, we will be starting our stopwatch. It took 4.84 seconds. It took 4.84 seconds. So as you can see, it is 4.84 seconds. Now students, you can remember in the previous one we took a little less time than this for the reaction to give us a color change. Now since in this particular reaction it took longer for us to observe the color change, it is very clear as we decrease the iodide ion concentration, the rate of the reaction slows down. As we decrease the iodide ion concentration, the rate of the reaction slows down, right? So the time taken for the color change to happen will increase as we decrease the iodide ion concentration. Let's move on to the third reaction. Students, now we move on to the third reaction. In the third reaction, we will take only 4 cubic centimeters of our potassium iodide solution. So the iodide ion concentration in the final reaction mixture will further be reduced. And in beaker 1, we will take 1, and in beaker 1, we will take 25 cubic centimeters of acidified Fe3 plus ion solution. And apart from that, 15 cubic centimeters of sodium thiosulfate and 6 cubic centimeters of distilled water will be taken as we have decreased the volume of I- ions that we take into the medium. So we will be adding our sodium thiosulfate, 15 milliliters of sodium thiosulfate solution into beaker 2. And then we'll be adding our 6 milliliters of distilled water into beaker 2 as well. Now beaker 2 initially contained only 4 cubic centimeters of potassium iodide solution. So now after addition of 4 milliliters of distilled water, it came up to 10 cubic centimeters, and after addition of our sodium thiosulfate solution, it came up to 25 cubic centimeters. So when we mix these two solutions together, the total volume would be 50 cubic centimeters. So now students, let's place this beaker 2 on our magnetic stirrer, and then we'll turn on the magnetic stirrer, and after that we can add our starch solution as well. We have to add few drops of starch solution, around 5 drops of starch solution, and then we will prepare our stopwatch, and we will add contents in beaker 1, which is Fe3 plus ions, into the beaker, and as soon as we add, we will start our stopwatch. Now students, the time is 12.12 seconds, 12.12 seconds. So you can observe the time here, 12.12 seconds. Now after noting down the time, we can move on to the next and the final reaction. Now students, we move on to the final reaction here, and in this reaction we have taken 25 cubic centimeters of acidified Fe3 plus ion solution into beaker 1, and to beaker 2 we have only taken 2 cubic centimeters of potassium iodide solution. So this potassium iodide solution has a concentration of 3 moles per decimeters cube. We only have taken 2 milliliters of potassium iodide solution into beaker 2. And into beaker 2, like we did in the previous instances, we are going to add 15 milliliters of sodium thiosulfate solution. Now the volume in beaker 2 is 17 milliliters. And then to increase the volume up to 25 milliliters, we will be adding water. We have measured 8 milliliters of distilled water. So we'll be adding this 8 milliliters of distilled water to the beaker 2. So 17 milliliters plus 8 milliliters would be 25 milliliters. So we have 25 milliliters of solution in beaker 2 as well as 25 milliliters of solution in beaker 1. Apart from that, we'll be adding 5 drops of starch solution as well. After that students, we will place this beaker 2 on the stirrer, and then we'll turn it on. And now we can move on to adding our Fe3 plus ion solution, and as we add, we will be starting the stopwatch. Now students, the time taken for this reaction to show a color change was 49.19 seconds. As you can see over here, the time taken for the color change to take place was 49.19 seconds. Now students, as you observed, when we kept on decreasing the iodide ion concentration, the time taken for the same observation to appear increased. So this is indicative of the fact that iodide ion concentration is important when it comes to deciding the rate of the reaction. So this means iodide ion concentration is not going to have a zero order. And when it comes to Fe3 plus ion concentration, also we made the same observation. So therefore, Fe3 plus ion concentration is also not going to be a zero order reaction. With respect to Fe3 plus ions, the reaction order is not going to be zero. So we can calculate the actual order of the reaction with respect to Fe3 plus ions as well as with respect to I minus ion concentrations when we move on to the next part of our experiment. So after making sure you take down all of the readings we have obtained in this experiment, it is time for us to move on to the next part of our experiment. We will be moving on to the whiteboard and we'll be calculating the order of the reaction with respect to both Fe3 plus ion concentration as well as I minus ion concentration, and afterwards we can move on to developing our rate expression for this reaction. So students, that will be all for this experiment. I will meet you again in the next part where we'll discuss these theory parts and carry out the necessary calculations.